All. So in the next few tutorial we will be discussing about implementation of neural networks on FPGAs and specifically on the Zinc platform. I'm not going to discuss the basics of neural network. I hope many of you know about it. Those who do not know about it, maybe you can visit some tutorial. Especially this website is quite good one, neural networks and deep learning.com. This is where I learned about neural network for the first time. So it gives a detailed tutorial, and it also gives an example of neural network, how we can detect handwritten digits using neural network. Okay. For that, they will be using a data set called the MNIST data set, and they're also giving a lot of Python code which can do it for you. Okay, so this gives a good background information. So I guess you will go through it, those who do not have background on neural network, and get a brief idea about what neural network is. You don't have to understand all the low level details, but it will be good if you can understand when I say like training or back propagation, activation function. Some of these terminologies you will be able to find from this one. Again, I'm not assuming any particular math background that is required for neural network when we do it on FPGAs, because we'll be reusing a lot of concepts from this software implementation. So even if you don't understand all the math behind it, especially the training part, the back propagation algorithm, it is still fine. Okay, so in this first tutorial I'm again just going to give you background, what are the important concepts when we are targeting a hardware implementation of neural network, how it is different from this software implementation. That is the main focus in this first tutorial, and in the subsequent one we will be looking at the actual coding and verification. So we are beginning with a fully connected neural network. Again, what is a fully connected neural network? We can read in that website, or here I have the picture. So in a fully connected neural network, you will see like every neuron in a particular layer is connected with every other neuron in the previous layer. Okay, so this is like a 4-layer neural network. We have input layer, output layer, and 2 hidden layer, and every neuron in these hidden layers as well as the output layer is connected with every neuron in the previous layer. That is what we call as a fully connected neural network. This is also a feed-forward neural network. That means the information, it always goes only in one direction from input layer towards the output layer. There is no feedback from one layer to the previous layer. So we have other kind of neural network like a recurring neural network where we have feedback mechanism that we may discuss in later on. So this is the simplest neural network, but for many applications these neural networks are quite useful. Now, as I mentioned before, when we usually design a neural network, there is a part called the training of the neural network, where you have to decide what are the different weights as well as the biases for the neurons involved in the neural network. Now, when we go for hardware implementation, especially FPGA implementation, in most cases we'll be using pre-trained network. That means we are not going to do this training part in hardware. Instead of that, we'll be doing the training in software. We get these biases and weight values. Then we use those values to design the hardware. Now, there are many reasons why we are not doing training in hardware. One of the most important one is for building a circuit which actually does training, we need a lot of resources, and the algorithms like backpropagation algorithm, which has differential terms and all, that is not very hardware friendly. Okay? It's quite difficult to implement, and even if you implement it, as I mentioned, we need a lot of hardware to do it. And in most cases we have to do training only once for a particular neural network. So if you do it in hardware, again, that is a resource wastage. After training, we don't need that part of the circuit, so it remains there, which is a lot of resources finally, which will be consuming no more power. And in many applications this training is not a time critical thing, because one motivation for using hardware for neural network is for acceleration, to do things faster. Now training is not a part of it, right? You do training once, It doesn't matter how much time it takes, maybe 1 day or 2 day. You do the training and you are doing it only for one time. Now, once you translate it to an actual neural network implementation, what we are looking at is a real-time performance in detection or classification kind of problems. That is what is time critical. So it's okay to do training in software, then do the real-time operation in hardware. Okay, these are general cases. There may be exceptional cases where you have to do training on the fly also. In that case, we will have to do training in hardware. But for the particular implementation that I am going to do, the training is done in software, and we'll be using pre-trained network for hardware implementation. Now, another important thing or issue when you go for hardware implementation is how you are going to represent numbers in hardware for neural network. Now, the input to the neural network, they are usually positive numbers. So these inputs can be pixel values or sound sample depending upon what kind of neural network you are building. In most cases, these inputs are positive number. Now, the weights and biases, they can be positive or negative number. Okay, and these numbers, input as well as weights and biases, they all will have a fractional part. They are not usually integers in most cases. Okay, now when you have this fractional part, we have two choices to represent it. We can either go with the IEEE floating point representation. There itself we can again two choices for 32-bit representation, we call it as a single precision implementation, or 64-bit implementation called the double precision implementation. So based on whether 32 or 64 you will have more precision, you can represent larger number. That is one choice. The other choice is called a fixed point representation of the numbers. So these are the two choices. Now, floating point representation, you can look at it, those who haven't seen it before, how numbers are represented in floating point using IEEE standard. Now, the advantage here is using IEEE format, you can represent very large numbers using floating point, okay, 32-bit or 64-bit. And the challenge here is the implementation and manipulation of floating point numbers are very difficult. Okay, in this representation, you cannot just go ahead and just add two numbers if you want to add them. We have to do some operations before you can add numbers together. Addition is especially challenging. Maybe multiplication is easier in IEEE representation. And for doing all these manipulation, again, we need a lot of hardware. That is the main challenge. So if you go for IEEE representation, the number of neurons that you may be able to implement in a low-end chip like the Zinc 20 chip in our Z board, it may be a few tens of neurons. That's all you can implement. But for a practical neural network implementation, you may need maybe hundreds of neurons. Okay, so that's why we don't prefer floating point representation, because of their resource consumption. So we'll be going with so-called the fixed point representation for representing all the numbers. And in neural network, again, mostly the input to the neural network will be always normalized, either between 0 to 1 if they are always positive. If they are negative, we will normalize them always between -1 to 1 plus 1. So it's okay to go with fixed point representation because the range of numbers are not that huge. That is one advantage of IEEE representation. You can represent very large number, but here we usually don't need very large numbers. Small numbers are good enough. So fixed point representation also works. But the small drawback of fixed point representation is the loss of accuracy. I will show you with an example. Because of the fixed point representation, that may bring a slight error in the calculation, maybe 1 or 2% error compared to the floating point representation. And again, for most applications, that is acceptable, these kind of small errors. But we'll be able to minimize that small error also by choosing appropriate fixed point representation. Now look at the example here, how we represent things using fixed point representation. So when you go for fixed point representation, you need to define few things. You need to define like what is the total number of bits that you are going to represent the number, and out of these, how many bits will represent the integer part of the number and how many bits will represent the fractional part of the number. And you are free to choose any number. You are not restricted by 32 or 64. You can choose any number. For example, here I am taking an example of 15-bit representation, and I am saying like out of these 15 bits, 5 bits will represent the integer part of a number and 10 bits will represent the fractional part. Now by making such definition, you are restricting what is the maximum range of the number that you can define, especially using that integer part, and you are also defining what is the precision of your representation, mainly using the fractional part. So 15.84, I'll be representing something like this. So this is 15 using 5 bits. So once you define like you will use 5 bits for integer, you should always use 5 bits to represent that integer, even if it requires less number of bits. And these many bits represent the fractional part, 0.84. Yeah, so this is what we call as a fixed point. So the position of this point, the decimal point, is always fixed here. It is always after 5 bits. That's why we call it as a fixed point representation. Now in floating point representation, the position of this decimal point is not fixed for any number. It moves around depending upon the number you want to represent. That's why we call it floating point. The point is floating. Now, in this representation, okay, so this number is supposed to represent 0.84, but if I really look what it represents, it doesn't represent 0.84, it is actually representing 0.83984,375 in decimal. So there is a error induced, which is like 0.000015625. That much error is induced, which is quite small if you see. It is less than 2 to the power of 10 to the power of minus 4%. So if you look at a standalone number, that is fine, but especially in neural network kind of scenarios where you keep on multiplying and adding numbers, this error will accumulate and it may affect our performance. So we need to choose our representation, especially total number of bits and how many bits for integer and fractional part very carefully. For that, we should be aware of what is the range of the input that we are expecting, what is the range of weights, what is the range of biases. Based on that, we'll have to choose the appropriate representation. Now, same example as before, if I choose like 10 bits for representing my number, out of that 5 bits for integer and 5 bits for fractional, same 15.84 will look something like this, and this again represents 15, and this fractional part is only representing 0.8125 instead of 0.84. So now you'll see like the error is increasing. Okay, so basically the more number you have to represent the fractional part, the more accuracy you will have. And of course, you should have enough bits to represent the largest integer part that you are expecting. So by fixing the number of bits, what you are basically doing is a trade-off between the accuracy and resource utilization. Okay, so the larger the total number of bits that you are going to use, the more will be the actual resource utilization. But better will be the accuracy. The smaller, vice versa. Now, as I mentioned before, inputs are generally positive, but your weights and biases may be positive or negative. So there should be some way to represent negative numbers also. So a traditional digital circuit, like you can either go for sign magnitude representation or 2's complement representation. Okay, I guess most of you are aware of these two representations. So in sign magnitude representation, the most significant bit, the leftmost bit, it will represent the sign. If it is 0, that represents it's a positive number. If it is 1, it's a negative number. And remaining n bits will represent integer part, and some m bits will represent the fractional part. Same as before, same example as before. Now I have 5 bits for integer part, but out of that 5, 1 bit is actually used for sign. So 1 bit for sign, 4 bits for integer, remaining for fractional. So if I compare these two numbers, just by looking at this bit, I will say like this is a positive number, then this 4, that is 15, and this remaining, that is 0.8398. Okay, so that represents plus 15.839. Same way, I just change this bit from 0 to 1, I have minus 15. So the bit pattern remains exactly same except for this ms bit. That is what is sign magnitude representation. Now it's very easy for us to decode from sign magnitude to decimal number for humans, but it has many drawbacks. Okay, one of them is it has two representation for 0. We can have plus 0 and minus 0, right? And that is one issue. But the major issue is when you do arithmetic operation with sign magnitude number. So if you add two sign magnitude represented numbers, it doesn't guarantee the result will be in sign magnitude. Okay, so that's a headache. That's why we have introduced this 2's complement representation. I guess you know about it. So 2's complement is nothing but you take 1's complement of a number and add 1 to it. So again, in 2's complement number also, if you look at the ms bit, you will be able to tell whether it is a positive number or a negative number. If the ms bit is 1, it's a negative number. If ms bit is 0, that is a positive number. And other advantage, of course, you can go ahead and read about it. 2's complement, because obviously it's not a course on digital circuit design. I'm not going into the depth. So look here. So again, in 2's complement representation, plus 15 will 15.839. It will look exactly same as before, but minus 15 point, it will look something like this. But by looking at this bit, I can say this is a negative number. So I will write negative. Now to really find the number, I will have to take 2's complement of this number. So you flip all the bits and add 1 to that, and you will be getting this number. So this is the one which is representing minus 15 point. Okay, so for addition as well as subtraction, which is basically addition only, 2's complement representation is very efficient. But for multiplication, 2's complement may not be very efficient, because again, if you multiply two 2's complement numbers, it doesn't guarantee the result will be also in 2's complement format. Okay, so we'll have to do some manipulation there so that the result also follows 2's complement. We'll see it when we do the coding. So that's about number representation. Final thing is on so-called the activation functions, which we'll be using inside our neurons. Okay, and many neural networks, the neurons are using non-linear activation functions. The recent one like ReLU and all, they are linear one, but many neural networks, again, our example will be using the non-linear one. In that website also you will see they are using non-linear one, which is a sigmoid function with this representation 1 by 1 plus e to the power of minus x, or sometimes we use hyperbolic tangent function also with this representation. Okay, so these are non-linear one, and if you try to really implement them in digital, that's very challenging. You may see research papers which are proposed to do this in digital domain using Taylor series expansion and all, but when we look at a practical point of view, this is not very practical. Again, main challenge is resource utilization. You may be able to implement it, but just one neuron is not enough for you. You may need hundreds of neurons, and you won't be able to share this implementation among multiple neurons. Okay, so that will take a lot of resources. Again, you won't be able to implement many neurons inside our Zinc chip. So that's why we go with the so-called the lookup table implementation. Again, this lookup table, don't confuse with the FPGA lookup table, which is a basic building block of FPGAs. This lookup table, or LUTs, this is a very popular technique in digital design as well as in software design also. So what you do is you pre-calculate these values 1 by 1 to 1 plus e to the power of minus x for different values of x. Okay, so for doing it, you should again have some idea about the range of x. Okay, so the input. So you should have some idea what is the range of x. Based on that, you pre-calculate all the values of it, and you represent it using our 2's complement format or sign magnitude format, whatever we choose, in binary, and we store it in some ROM. Okay, and the address bus to this ROM will be this x. So when we give x to that ROM, he will give me the pre-calculated value, whether it is sigmoid or hyperbolic tangent, whatever it is. So these ROMs are what are called as lookup tables here. LUTs. Again, we will see in coding how it is done. Another last topic is about using IP cores when we are going to design our neural network. So we generally won't instantiate, especially in my sample case, we are not going to use any Xilinx IP core directly. That is mainly to make our design more flexible, because if you use Xilinx IP core and if you want to change some parameter, for example, I used a lookup table for implementing the activation function. Later I decided like, okay, the size of the lookup table is not enough, I need to increase the size. You cannot just change it by changing a parameter in Verilog. Instead of that, you will have to go to this Xilinx core generator and you will have to change it in the .xci file. Okay, so that makes our code not very flexible. That also make our code not very portable. For example, if it is in pure Verilog, you can implement the same neural networks in Intel FPGA or Lattice FPGA also. You don't have to go through the core instantiation or something like that. It becomes very portable across any FPGA or even for ASIC implementation. Okay, so that's why we are not going to use any Xilinx IP core. But these Xilinx IP cores are very efficient in implementing hardware. For example, again, if I take the example of lookup table, we have two choices. We can build them either using block RAM, which are the built-in primitives inside Xilinx FPGAs, or you can build it using so-called the distributed RAM, which is basically built by combining lookup tables and flip-flops. Now, block RAMs, their clock performance is much higher than distributed RAM, and we usually prefer block RAMs for implementing these kind of ROM. So what you need to do is we need to follow certain coding style so that Vivado he automatically understands that I am trying to infer this particular primitive. Okay, so if you follow that coding style, he will automatically instantiate block RAM, he will automatically instantiate DSP slices, etc. So again, that style also we will see when we do the coding. Okay, so that's all in this introduction. So in the next tutorial, we'll start our coding. Thank you.